All right, it's 11:15. I think we'll get started. So I'm working my way through grading the written part. I'll have that sorted out in the next week or so. So just hang tight. It's a good thing to check that your written part was submitted. If you didn't get it submitted, shoot it to me by Canvas email. Stuff happens. But I'll work through the exam. I didn't hear about any super major issues in the exam, so I assume there weren't any, but if there were things that got off track, just hit me up in office hours next week. That's where I want to discuss the exam. Also, take a look at the final schedule. It's going to be on Canvas. The final is going to look exactly like a regular exam, just a little bit longer. So make sure you schedule yourself like 2.5 hours to take the final. And it's going to be open for multiple days in the finals period, probably Thursday and Friday, maybe even Wednesday and Thursday and Friday, depending on what I hear. But our schedule is set from now till the end of the semester. So make sure you get exam number 4 on your calendar. Take a look at the syllabus. So we have one more regular exam, and then we have the final. So it's a good time to mark those dates off. Make sure that you're up on all that stuff. Any questions or issues or things people want to talk about before we get started? Okay, so we're in the next section, and so you can get the notes online. And so in this section, we're going to talk about mixing polymers, or how polymers and solvents mix together. So you can get out your clickers right now. And so we start with mixing with this concept called an ideal solution. If I can draw. So ideal solution is a vocab word, and there's 2 assumptions in an ideal solution mixing. So everyone knows what we're talking about. We're mixing 2 different molecules. So water and ethanol, or we're eventually going to mix like polycarbonate and polysulfone. We're going to be mixing polymers, because it turns out that a lot of polymers that we use industrially are mixtures. So it would be nice if they were all homopolymers, really easy to understand. But real products are either copolymers, or they're copolymers with filler in them, like silica or clay, so it's composite, or they're polymer blends or polymer mixtures in order to get exactly, or a combination of all those, to get exactly the right properties that folks need for their products. And so polymer mixing is also really important when you want to dissolve a polymer in solvent. Why do polymers dissolve in the first place? What are the interactions? All of those things. And that's what we'll talk about in the next couple slides. So an ideal solution is defined as solute and solvent have exactly the same size. That's a definition of an ideal solution. And the second definition is that all intermolecular interactions are equivalent. That's a very interesting one, because it means that whatever intermolecular interactions you have in the red, I guess the solvent, and whatever intermolecular interactions you have in the solute, when those are separate, you have the exact same intermolecular interactions when you combine the 2. So these 2 concepts define ideal solution. So here's the clicker question. Oh, let me start the clicker. I think we're still on CD, so let's go with that. So if we mix a solute and solvent, if we try and think about a process, it's good to start with the Gibbs free energy, right? You all know this equation, you've all memorized it. And so if we have equal intermolecular interactions between all our components, what's the delta H of mixing for an ideal solution, or what's the enthalpy? And when you think about enthalpy, sort of what comes to the top of your mind? Heat. That's right. It's not exactly the same. There's many different types of heat, but enthalpy is sort of just a mathematical construct in thermodynamics. You can get a feel for it if you think about heat. And so how is heat generated in solution? Different intermolecular interactions, right? And so based on the definition that all components in an ideal solution have equal intermolecular interactions, there's no heat released or heat taken up or energy released or energy taken up when you make an ideal solution. So delta H of mixing has to be 0 by definition. And so, you know, when you take, let's say, sodium hydroxide and dissolve it in water, you've got very strong intermolecular interactions in that solution, and the water gets hot or the solution gets hot. That's a non-ideal solution. Okay, we got that. So that's a key concept, that all intermolecular interactions are equivalent, so no change in potential energy or no change in molecular interaction energy upon mixing. So what do we know about delta G? What's your sort of feeling for different values of delta G? If delta G is 0, what do we know? Well, not quite. If it's 0, what do we know about delta G? We're at equilibrium, right? Delta G equals delta H minus T delta S. This will probably be on your equation sheet, but you should just memorize this. So if delta G equals 0, then we're at equilibrium. That's always true. If delta G is less than 0 or is negative, what do we know about whatever process we're describing? Spontaneous is an okay word. Let's say it in full scientific language. If delta G is less than 0, it's thermodynamically favorable. The reason I don't like spontaneous, even though that's how it's taught oftentimes, is that spontaneous gives you the feeling that it just happens instantaneously. Spontaneous, instantaneous, kind of gives you the same feeling. However, things that happen quickly are due to kinetics, which has nothing to do with delta G. And so we're talking about thermodynamics here. And so thermodynamics is, where are we going in terms of the total energy or the potential energy or the Gibbs free energy of the system? Kinetics is, how fast is the process happening? And so I much prefer to say, if delta G is less than 0, this is a thermodynamically favorable process. We need to build in the kinetics to figure out how fast it's going to happen. Okay, and if delta G is greater than 0, if delta G is positive, what do we know? It's thermodynamically unfavorable. And I like that nomenclature because what is the thing that we can change pretty easily to make a process favorable or unfavorable? How do we change the sign easily of delta G? Yes. Change the temperature. That's right. Because delta H can be positive or negative. Delta S can be positive or negative. And so T, remember temperature is in Kelvin for these equations or this unit. T is a handle that we use in order to change the sign of delta G. And that really depends on the sign of delta H and the sign of delta S. Okay, so I would prefer if you remember these things about delta G. And so if a process is thermodynamically favorable, is it going to happen or not? Yeah, eventually it will happen. You know, eventually, we just don't know how fast it will happen. Yes. Whoop, I'm signed out. Well, that's interesting. I wonder what I'm signed out of. Let me go back. All right, that looks good. Obviously this thing's working. Okay, let's just give it a try, see what happens. So that was the most important slide anyway. So remember these rules and think about in terms of, will it happen, won't it happen versus kinetics. All right. Let's see. All right. Here's another clicker question. So we're mixing this solute and solvent again, or two different molecules. We don't have to call it solute and solvent. We could just say we're mixing two molecules. What is true of delta S of mixing? So I should say that this little subscript means mixing. And notice delta S is change in entropy. And so the changes from the red circles and the blue circles separate. So let's say in two separate beakers, and then you take those and then you mix them. What is the change in entropy from those two states? Because you're always calculating between two states. So based on this, if you start with the red circles separated from the blue circles, and then you mix them together, what sort of concept comes to your mind when you think about entropy? Randomness, disorder, things that are more disordered generally have more entropy, right? And so if you start with nice separated circles, there's a lot of order there, right? Things are with their own kind. And then you take those and mix them all up, you have increased the disorder, or delta SM is greater than 0. Oh, let me put it right here. Increased disorder. And that's true for almost all mixing processes, right? You have nice pure components, and then you mix them together and the disorders increase. All right. Got that. All right. So we put those two things together. And one more clicker question and before we start talking more. What's true of delta G mixing for an ideal solution? Now that we know what delta H is and we know the sign of delta S, what's true about delta G? We're at 45 before. I'm looking forward to getting back there. Great. So it's really easy to just write this out. Delta G equals delta H minus T delta S. This is 0. T is always positive, right? It's in Kelvin, so that's always positive. Delta S is positive as well because we're increasing the disorder. Let me make that a better positive sign. So delta G is always going to be less than 0 under these conditions. And so that means in an ideal solution, great, 48, perfect. In an ideal solution, the delta G is always less than 0. It can't be anything else because we're always going to increase the entropy and we're always going to have delta H of 0. So that means an ideal solution is always thermodynamically favorable to form. We can't think of another situation where that's not the case, unless we start to change what delta H is, but then we don't have an ideal solution anymore. Is everyone okay with that? Yeah, so if we change delta H, it's not an ideal solution. We're out of that regime. All right, so that's really important to think about because for any chemical process, you could take a shot at figuring out what the sign of delta G is, and that tells you a lot about the situation. All right, it turns out that you can calculate the entropy exactly in this really simple example, and it's given by this capital omega right here. You don't have to worry about this too much. I mean, we're not going to plug and chug exact entropies for this checkerboard situation. You do want to know that the Boltzmann equation does give you the exact entropy. That always works, right? Depending on how you calculate capital omega, you can calculate the Boltzmann distribution exactly. And we won't derive this, but for a chemical system that is ideal solution, this is the entropy of mixing, and this is the Gibbs free energy of mixing. And you've got mole fractions. So rather than talking about checkerboard positions, which is this, you've got mole fractions and you have number of moles. So for a chemical system, you know what all that is. So how did we go from using K in the Boltzmann equation to using R? What's the difference between K and R? It's right on the bottom in case you forget, right? R equals K times Avogadro's number. So K works if you're counting particles or molecules. I have 10 molecules, I have 50 molecules, I have something like that. R works if you're calculating based on molar quantity. So we have mole fraction and number of moles, so we have to use R. What value of R do we use in this equation? I mean, if I stopped you on the street and I said, you know, what's R? You would say, well, it's the ideal gas constant, right? We use it to calculate volumes of ideal gases and number of moles and everything else. But how is R used in Gibbs free energy? What's a good unit to think about in terms of R? It's got a bunch of different units, right? If you look up ideal gas constant on Wikipedia, there's like 10 different units that R can take. What's the one that we want to think about? Yeah. Joule per mole K. So R equals 8.314 joule per mole K. And that looks a lot less like how many moles of ideal gas are in a given volume. And it looks a lot more like an energy per mole per degree temperature. That's really interesting because now R at its core is really a unit of energy or a descriptor of how much energy is available at a given temperature, just like K is. And that's why we talk about KT, the molecular energy available at a given temperature. R times T gives you joules per mole. That's really interesting. Tells you how much energy is around at a given temperature. So think about that. That's a really important concept for going between, you know, the easy ideal gas stuff. When is that appropriate? Versus thinking about R and Gibbs free energy in this context and in terms of how much energy is around at a given temperature. And if you look at the units, it's easy to break it down, right? You know, lots of things in terms of kilojoule per mole, reaction energy, kilojoule per mole, bond dissociation energy, kilojoule per mole. R gives you kilojoule per mole if you know what the temperature is. And if you raise the temperature, what happens to the available joules per mole? Goes up, right? That's why oftentimes if you can't get a reaction to happen, what's your first instinct? Oh, nothing's going on. My reaction's not happening. What do? You raise the temperature, right? You raise the available energy so your reaction can hop over the activation barrier, whatever you're trying to climb. That's how raising the temperature works when you want some process to happen. Most of the time, that's okay. Sometimes that doesn't work because you make the Gibbs free energy more and more positive, but that's a exception. Okay, enough about that. These are important. And remember, this is for ideal solution. And this idea about what the gas constant really means is something that you want to take forward with you. Any questions or comments so far? Okay, don't forget to check the box folder, download the notes. There will be more notes coming in this section. And so again, if you can't find them, the box links are on Canvas, but hopefully you're in the groove with that. All right, so we don't care that much about solute and solvents in this class because we really care about polymers. And so the question is, are polymers ideal solutions? And the answer is no, they're not ideal solutions because we violate the two assumptions, right? Solvents like benzene, acetone, water, you know, all those things that you learned in organic chemistry, those are small molecules. And polymers are big. One of the assumptions that we'll make is that a solvent molecule is about as big as one monomer unit. And that's pretty reasonable, right? Because some solvents like benzene look a lot like a styrene repeat unit, right? So we can sort of imagine that the spheres that we use to, or the circles that we use to represent the polymer repeat unit are about the same size as the solvent. So we can use some of this simplified mathematics. Also, intermolecular interactions are important. And so I'm going to take the simple example of you have some sodium chloride and you want to dissolve it. If you take that sodium chloride and put it in oil, what happens to the sodium chloride? So you put it in mineral oil. Nothing happens. It's not soluble in mineral oil. Because the intermolecular interactions of the sodium chloride are stronger than the intermolecular interactions between oil and sodium or chloride. So it doesn't prefer to mix just based on the intermolecular interactions. And if you take sodium chloride and put it in water, of course, the intermolecular interactions between sodium chloride are very strong with water. And so you get solvation of those ions and it dissolves. This also works for polymers. You want to dissolve polymers in things that look like the chemical structure of the polymer. So we need to remember, like dissolves like. Why isn't polystyrene soluble in water? It's all carbons, hydrogens, it's a hydrocarbon, right? It's not polar. Polystyrene has very low polarity. So if you just look at this, remember we have water. I'm not going to draw these to scale. Water is obviously really, really small compared to our big old polystyrene, right? PS is not so there's a big polarity difference. And so if we had to pick a solvent for polystyrene, what could you imagine could be a good solvent based on your knowledge of organic chemistry and all the small molecule compounds that you've studied? What could be a good solvent? Yeah, benzene. Oh, good solvents. What's another good solvent? Toluene, good one. Much less toxic than benzene. Any other good solvents? Naphthalene, yep, maybe the double ring structure. Another good solvent for polystyrene is the monomer. Turns out that styrene is a liquid and it's a great solvent for the polymer. And that's a trick that the polymer industry uses when they synthesize polymers or when they dissolve polymers and do something else with them, is you can use the liquid monomer as a good solvent sometimes. Okay, good. We're on the same page there. So The size assumption is wrong and the intermolecular interaction is wrong, but we start with ideal solution to get our bearings on what's happening with delta H and delta S, and we're going to use those concepts now to describe polymers. So the way that we describe polymer solutions is called Flory-Huggins theory, after Flory, who's a Nobel Prize winner in polymer physics, and Huggins, who doesn't have a Nobel Prize, but is memorialized with Flory in this name. So when we mix polymers and solvents, or when we mix two polymers, Flory-Huggins is a theory where we start. So this is in all the polymer textbooks. It's discussed in your book. So, you know, if you're feeling like these slides are a little bit esoteric, this is a really good time to crack open the textbook or click on the textbook link and actually read through this, how these equations are developed. Okay, so because we said that the monomer unit size is the same size as the solvent in our assumptions, we can still write this checkerboard, except now the polymer, which we're going to denote in blue color here, if you can see that, is connected because it has to be. It's a polymer with a certain molecular weight. This is what defines polymers that we started with on the first day. And so if we think about the mole fraction or the combinatorial entropy of mixing, you know, what's the, well, let me skip to this slide. So if we just went with mole fractions, how many moles of polymer or how many polymer molecules do we have in this checkerboard? One polymer molecule. And how many red circles do we have on this checkerboard? Red ones? We have 100 places total. Turns out we've got 75 red circles. And I know that because the total is 1 plus 75. So based on the area of this checkerboard, you know, the polymer is taking up 25% of the area, right? And the red circles are taking up 75%. But if we calculate the mole fraction, it's one of the polymer, it's 1/76, which is very misleading, right? The polymer is taking up significant space, yet its mole fraction is really low because its molecular weight is so high. And so in order to get a more accurate representation of the mixing problem, we use volume fraction. And so the volume fraction, of course, there's 100 volume units in this checkerboard. The volume units are just two-dimensional squares, and the polymer is taking up 25 of those. And that's a much more representative picture for how much polymer is there versus how much solvent. And so one of the hallmarks of Flory-Huggins is that we're going to use volume based fractions rather than mole fractions. So if we go back, bless you, if we go back to small molecules, right, where we have no polymers in an ideal solution, remember, ideal solutions are not about polymers because we violate the assumptions that the molecules are the same size. We can use mole fractions and number of moles because everything's the same size. So this gives us an accurate picture of how many red circles and blue circles are there. In order to get that same accurate picture, what Flory and Huggins did was they came up with this idea of volume fractions in order to represent how much polymer is there and how much solvent is there. And so the really important thing that you have to remember in this unit when we start to mix polymers, when we start to describe polymeric systems, is we're going to have volume fraction based calculations for polymers. And this will stay with you in your advanced polymer classes where you use Flory-Huggins theory to describe block copolymers and other sorts of phase diagrams in polymers. Most polymeric quantities are based on volume fraction, not mole fraction, because the molecular weight's so high. All right. And so we just modify now our delta S of mixing for polymers. To take into account the volume fractions. So when we compare and contrast, ideal solution theory based on mole fractions, Flory-Huggins theory based on volumes. So that's a step that we want to make, today and when we meet on Monday again, is that we are able to figure out, or at least able to square up, what's happening in small molecule ideal solutions versus what the difference is with polymers. Okay, any questions or comments on that? I know this is a little esoteric getting started, but it'll get more and more real. And then eventually we'll do some calculations. And I think I posted the homework for you. You can take a look at that, figure out where we're headed in this week. But of course, homework's not due till next Friday. No homework due today. I think there's a PLA due today, but I made it due tonight. So just make sure you get that PLA done. Yeah. Then we'll be in regular PLA space the next couple of weeks. All right, we already covered that. So this is just a little example with numbers where we take our number of moles and mole fraction, and then we take our number of moles and volume fraction. And this now is just the entropy part. We still have to figure out this enthalpy part because we said that like dissolves like, so the intermolecular interactions are going to be important in polymers as well. So we've got lots of different intermolecular interactions to pick from, right? We've got our London dispersion forces, we've got dipole-dipole forces, and so when we talk about polarity, we're often talking about what has dipoles and what doesn't. Of course, everything has dispersion forces. Those are important. And then we can figure out some of the other forces, hydrogen bonding, which is kind of like dipole-dipole, only more localized. And so by examining the molecules, by sort of looking at water, looking at benzene, looking at styrene, we're already used to thinking about, okay, these are probably the intermolecular interactions going on. And so I'm probably only going to have dispersion forces in polystyrene. I don't see any strong dipoles in there. I don't see any ions. I don't see anything else. So I just have dispersion forces there. I know that water is polar and it has hydrogen bonding. And so I can start to figure out if I'm going to have compatible solvents and compatible polymers. All right. So we're not going to get too much into the other types of intermolecular interactions, but you can recognize polarity when you see it. So the question is, we need to figure out how to account for this. So we have an equation for delta S in mixing, right? We could just plug that into the delta G, but now we need to figure out an equation for delta H. And so we have a bunch of different types of interactions in this system. So whenever you take two different types of molecules and mix them together, you always have what are called the pairwise or the same interactions or the peer component interactions. So you still have solvent-solvent interactions and polymer-polymer interactions. And we're going to talk about polymer segment. So this is and the polymer segment is kind of like the repeat unit. That's good enough for now. And then you have the crosswise interaction, you have the solvent polymer interaction. So all three of those things need to be accounted for when we think about what the delta H is. And so this can get complicated, right? We can talk about nearest neighbor and next nearest neighbor interactions. And so we make the nearest neighbor assumption that we can figure out what the interactions are between these two components by only considering the nearest neighbor interactions. And this is just an assumption that's built in to the delta H. There are other more sophisticated models for figuring out longer range interactions, but we're not going to use those. Okay, so in order to calculate this delta G or delta H, first we're going to work on the Gibbs free energy of interaction. We have G11, which is red circle interacting with red circle. So this is our benzene just sitting there in a beaker. There's no polystyrene in there, just waiting for something to happen, right? And so this is the intrinsic intermolecular interaction of our solvent-solvent. We have exactly the same thing for our polymer, or this is not yet a polymer, but these are the intermolecular interactions between two polymer segments. So this is polystyrene segments just sitting there interacting with itself. And so we don't denote that as G22. And so we have G11, we have G22. And then when you mix these, and we're going to assume good mixing, we've got G12, and we're going to call these the same thing because G12 and G21 are exactly the same thing. And so the change in energy based on this little algebraic or this little map that we have right here, the change in energy when one interacts with two is G12, our new interaction, minus 1/2 of our original interactions. Now we want to do this on a per mole basis, right? If we add this up, we'd have 2 G12 minus G11 plus G12. So this diagram gives us delta G12 equals 2 G12. I have 2 G12 interactions right there. And I have to subtract off my original interactions because I'm looking for the change. I've got a G11 plus G22. So this is original right here, but I want it per mole of interaction, or I want it per one interaction right here. So I divide everything by 2. There we go. So this is just thinking about the energy of interaction between all of these different components. And the one thing that you have to remember is this is a change in energy. So you have to subtract off the original, right? Because there is interaction energy in styrene and benzene as they're just sitting there. And you're looking for the change from one state to another. All right, and that's described right here. All right, one more slide. And then we'll have some discussion. So this can get complicated when we start to talk about real systems. And so what Flory and Huggins did is they constructed this thing called the Flory parameter, or this is often called the interaction parameter. And so it describes the interaction between a polymer and a polymer, or a polymer and a solvent. And it's all lumped together. I mean, it's made of these small G12s that we just came across. And once you define this interaction parameter, what Flory and Huggins did was define this expression for delta G of mixing based on the entropy part, the volume fractions, right? This is in there. And then the enthalpic part based on the interaction parameter, and it's all lumped together. So we don't necessarily calculate delta H and delta S separately in Flory-Huggins, but the delta H is built into is built into Chi. So you'll derive this equation in your higher level polymer classes. I think it's derived in the book, so you could check that out if you want. We don't need to derive it in this class. We just need to know, what are the phi's again? What's phi 1, phi 2? Volume fractions, always for polymers, volume fractions. And then we have our RT, we know what that is. We have to count how many moles of stuff we have, and then we have our interaction parameter. So we built up the same idea of, you know, how much space is the polymer taking up, what's the volume fraction, and what are the intermolecular interactions. And so instead of using ideal solution theory, we use Flory-Huggins, and then we start to think about, again, what is the sign of delta G? And if we can figure out the sign of delta G, or if we can figure out the magnitude of delta G, that gives us an idea of what's thermodynamically favorable and what's not thermodynamically favorable. Okay, so the clicker question is, which is more favorable for mixing, a high or low Flory-Huggins parameter? Remember, this is Chi right here. And so we need to look at this equation, delta G of mixing, and figure out some sort of sign for delta G. What's the sign of R? Positive, always. What's the sign of T? Positive, always. And so we look here, volume fractions, okay, moles, great. And the question is, if Chi is big or small, what is favorable for mixing? All right. Everyone got their answer in? And it turns out, if this Chi is a lower number, we get more negative, and let me say thermodynamically favorable mixing. So that's an important concept. And so if we want a lower Chi, or if we want more favorable mixing, we need to look for these low interaction parameters. And so when you talk about polymer mixing, this describes the idea of like dissolves like, right? So if you have very similar intermolecular interactions to your cross terms or your intermolecular interactions between your polymer and your solvent, Chi is going to be very low. And eventually, if you have the same intermolecular interactions between your solvent and your polymer, what's Chi? 0, right? So if there's no change in the intermolecular interactions as we do this mixing, Chi is 0, right? And that's an ideal solution. We know that's favorable. And so polymers that have similar polarity or similar chemical composition or similar functional groups, those will tend to mix because they're low Chi systems. Then polymers that are really different, like if we take let's take polyethylene. And we'll take polystyrene again, because we can never forget what these two polymers are. Will these mix? Why not? Yeah, this aromatic ring is not very compatible with the hydrocarbon backbone. Sorry, this PS. Not very compatible with the hydrocarbon backbone of polyethylene. And so this would, the Chi would increase because they've got different molecular interactions And so you wouldn't have as favorable mixing. Where does mixing polymers become really important? I mean, I talked about different products and polymer blends and other stuff in terms of getting the properties you want, but where is mixing polymers like at the forefront of people's minds right now? So it turns out that plastic waste is a really big problem, right? And recycling polymers is really hard. And so the reason that all those recycling codes are on the bottom of bottles and things that can be recycled is so we can separate those polymers. Because if you take a polyethylene bucket or something like that, and then you take a bunch of styrofoam, although that's hard to recycle because it's pretty light, or you take a bunch of polystyrene disposable glasses or something like that, you cannot get those to mix. And then you get really bad properties. So it turns out if you have polymers that don't mix, you can't get any good materials because it's just like, you know, mixing sand and mixing gravel. You know, if you take that, you've just got a mixture of stuff. They'll separate. You don't have any good properties from that. And it turns out that recycling polymers, polymer mixing is one of the most important properties to get good recycling. And people have invented new polymers to help with compatibilization, to get polymers to mix. And so polymer mixing is really important for polymer recycling. You know, they just don't put those recycling codes on bottles so they can tell what plastic it is. They need to get those different types of plastic in different recycling streams and treat them differently. I mean, granted, they all have different thermal properties, so they have to melt them differently. They have to go through different processes. But other than making really mixed plastic junk or really junky plastic wood, you can't do a lot with mixtures of polymers. And so that's one of the important technologies going forward is how do we improve polymer recycling by improving polymer mixing. Okay, I'm just going to leave you with this one example, and we're not going to study too much about polymer mixing except when we talk about polymer blends, but there's a lot of really interesting mixing phenomena that happen with polymers and water and polymers and solvents. And so we're going to talk about this here. So this is a new polymer that you might be interested in. This is polynipam, and you can try and pronounce poly-N isopropyl acrylamide. And so that's great. It looks like this. You don't need to memorize what the structure is, but this polymer is hydrophilic and hydrophobic depending on the temperature. So one thing that you do is as you raise the temperature of a polynipam in water solution, you can get the polymer to precipitate out of solution. Whereas if you lower the temperature, the polymer goes back into solution. And so we'll talk about that as you change the T in this equation, the delta G crosses zero, it goes from positive to negative. And so what does a polymer solution look like? So when you look at a polymer solution, you say, oh, this is a polymer solution. What is it usually? Nice and clear, right? You can't see anything in it. You say, oh, it's a little viscous, it has polymer in it. Nice clear solution. Polymers that come out of solution look like a colloid or look milky like this. And so you can tell that a polymer is precipitating when the solution gets cloudy versus the polymer's well dissolved when the solution is clear. And so we'll start here on Monday, but you can think about, okay, you know, what's happening with delta G? How do I know what's happening with the polymer? And we'll talk about this Monday. Have a good weekend. Don't forget about getting set up for the next exams and everything else. I'll see you on Monday. Yeah, you too.